Equilibrium 2, reaction quotient. The essential idea. Many reactions are reversible. These reactions will reach a state of equilibrium when the rates of the forward and reverse reaction are equal. The position of equilibrium can be controlled by changing the conditions. Nature of science. Employing quantitative reasoning. Experimentally determined rate expressions for forward and backward reactions can be deduced directly from the stoichiometric equations and Le Chatelier's principle. On the road to equilibrium. Have a look at this graph showing a reaction moving towards equilibrium. You can see we've got the reactants here. We've got 0.8 moles per litre reacting, and then it settles at 0.6, and we've got two products. We've got B, which after 4 minutes settles at 0.4 moles per litre, and C, which after 4 minutes seems to settle at about 0.2. What is the balanced equation for this reaction? Well, we've got A going to B and C, and you can see we've got twice as much B as we do C. So A is an equilibrium with 2B plus C. So what will be the equilibrium constant? Well, we put products over reactants, and the coefficients become the powers. So we'd have B, concentration of B squared, multiplied by C over A. At what time does an equilibrium exist? It's very clear that this is occurring at 4. If we would determine the value for the equilibrium constant, Kc, we would simply plug in to this. B would be 0.4, C 0.2, A 0.6. Do the maths, get the answer. If you use the concentration of 2 minutes in the equilibrium constant expression, how would your value compare to the equilibrium constant? 2 minutes, this bit, there, and there. So we have 0.32, about 0.15 I guess, 0.65 for the reactant. Plug in the numbers and you can see we get a different value. We've got 0.024, so it is smaller than the equilibrium constant. The reaction quotient. If a system has not yet reached equilibrium, the ratio of the concentration of product to reactants will not equal the equilibrium constant. This ratio is called the reaction quotient, and it helps determine the progress of the reaction. When Q is larger than the equilibrium constant, the concentration of products is greater than at equilibrium, and the reverse reaction is favoured until equilibrium is reached. If the reaction quotient is smaller than the equilibrium constant, then the concentration of reactants is greater than at equilibrium, and the forward reaction is favoured until equilibrium is reached. When Q equals the equilibrium constant, then the system is at equilibrium, and the forward and reverse reactions occur at equal rates. Here's a nice graphical representation of that. So when the equilibrium constant is greater than the reaction quotient, reactants will move, the rate of reactants forming products will be greater than products forming reactants, and you're moving towards the equilibrium balance. If the reaction quotient is greater than the equilibrium constant, then the rate of products forming reactants will be greater than the rate that reactants form products. And of course, when they are balanced, reactants and products are at equilibrium. A general equation for a system not at equilibrium is same as if it were equilibrium, you write out the same, but these values just aren't at equilibrium. They're not the equilibrium, they're not the concentrations at equilibrium. Okay, let's do an example. For the decomposition of antimony pentachloride, we've got an equilibrium constant of 0.0251, and we've got our reaction there. So what is the value of Q if SbCl5 is 0.095 moles per decimeter cubed, SbCl3 is 0.020, and the concentration of chlorine is 0.050. Well, you can write out products over reactants, just plug in the concentrations of each one and you get your answer. More interestingly though is, how will this reaction proceed? Well, we can see the Q is lower than equilibrium constant, so the concentration of product is too low, or the concentration of the reactant is too high. So the reaction is going to proceed to the right to reach equilibrium, or the forward reaction will be favoured until equilibrium is reached. Second example, we've got an equilibrium constant value of 4 for A2 plus B2, giving us 2AB. And we've got some lovely pictures here representing 3 reaction mixtures containing A2, B2 and AB. Obviously AB is the one where you've got a blue and red atom together. And let's just say A are the blue ones, B are the red ones. Which reaction mixture is at equilibrium? Well, we know the equilibrium constant is 4. We've got the reaction here, so we'd write out the equilibrium constant with the concentrations and put the coefficients as powers. Then we just plug it in. For 1 here, we've got 1, 2, 3, 4, 5, 6 ABs, so that would go on top as being the product. And we've got 1A, 1A2 and 1B2. So put it in, do the math, it's 36. For this one we've got 1, 2, 3, 4 ABs, put it in, and we've got 1, 2 A's and 1, 2 B's. Do the math, we get 4. The final one, so you can see it's 2 ABs and 3 A's and 3 B's. So we get 0.44. So obviously the central one, 2, is at equilibrium because the value of Q equals the value of K. For any reaction mixture not at equilibrium, in which direction must the reaction proceed to equilibrium? For 1, it's going to proceed to the left because Q is greater than Kc. And 3 is going to proceed to the right because Q is smaller. And that is the end of this presentation. Splendid.